All right, so lecture 32, applications of the first law. So as the title says, we're still looking at the first law of thermodynamics. Yesterday, we've learned what the first law of thermodynamics is. It's essentially the law of conservation of energy applied to heat transfer, where the change in the total energy of the system, which is given by the change in the internal energy, is equal to how much heat, how much energy is added to the system in the form of heat Q minus the amount of energy taken out of the system in the form of the work done by the system. Right. So we've learned this yesterday, what the first law of thermodynamics is. And previously in our previous lectures, specifically lecture 26, we looked at different thermodynamic processes that described how the pressure, the volume, and the temperature of a gas, of an ideal gas, changes. And we've learned, for example, Boyle's law, Charles' law, and Guy-Lussac's law. Boyle's law is when you have a thermal process that happens at constant temperature. Charles' law is when you have a thermal process that happens at constant pressure. And this is how the volume changes with temperature. And Guy-Lussac's law is tells you what happens when you have a thermodynamic process that happens at constant volume. Then we combined all these laws into a single equation called the ideal gas law. PV is equal to nRT. All right, which tells us, which essentially tells us what happens to the pressure, volume, and temperature of the gas if one or the other changes. So in today's lecture, we will see how the internal energy of a gas changes for each of the thermodynamic processes. So we'll see how the internal energy of the gas changes if you have an isothermal process. Isothermal is, of course, constant temperature, and therefore the change in temperature is equal to 0. We will look at how the internal energy of the gas changes during an isobaric process. Isobaric process is when you have a constant pressure, and hence change in pressure is equal to 0. We will look at how the internal energy of the gas changes when it undergoes an isovolumetric or isochoric process. A isovolumetric or isochoric means that the process happens at constant volume, and therefore the change in volume is equal to 0. We will learn a new process today called the adiabatic process, and this is where neither temperature, pressure, or volume is constant, meaning all three variables, temperature, pressure, and volume, changes, and we will see how the internal energy of the gas changes during an adiabatic process. We will learn more about what an adiabatic process is, but I've already stated here that during adiabatic process, there is no heat transfer, or Q is equal to 0. And so we will look at these 4 thermodynamic processes. They are usually represented using what we call a PV diagram. Okay, it's called a PV diagram because it's a graph where the y-axis gives you the pressure of the gas, and the x-axis gives you the volume of the gas. So in an isobaric process, isobaric is, of course, constant pressure. The gas pressure is constant all throughout the process, but the volume of the gas can change. All right, so in this particular figure, the volume changed from 10 to 2. Okay. Representing an isovolumetric process in the PV diagram looks like this. This vertical line here. In an isovolumetric process, the volume is constant. The x-axis gives you the volume, so you have only a single volume throughout the process, but the pressure can change. Right? So notice how you have two pressures for this isovolumetric graph. Okay? And in an isothermal process, the pressure and the volume changes. It's because it's only the temperature that's kept constant. So for an isothermal process, the PV diagram is represented by this curved line. So notice how the pressure changes. You have a PA and a PB pressure, as well as the volume changes during an isothermal process. But we'll look into each of these processes in more detail as we determine how the internal energy of the gas changes in each of the process. So the key equations we'll be using when we're analyzing these thermodynamic processes is, of course, the first law of thermodynamics, because we are applying the first law of thermodynamics to these processes and trying to figure out what's the change in internal energy for each of the processes. Okay. Also recall that the internal energy can be related to the temperature using the kinetic theory of gases. Okay, when we had the lecture on kinetic theory of gases, we said that the internal energy is essentially the total energy, total kinetic energy of the molecules, and that's directly related to the temperature. Okay. So we will be using these two equations interchangeably to find the change in internal energy. All right, are we ready? First process, the isothermal process. During an isothermal process, the pressure and the volume of the gas changes, but isothermal means the temperature doesn't change. Right, so if we represent the isothermal process in a PV diagram, y-axis is pressure, x-axis is volume. Right, the pressure, both the pressure and the volume changes. So you can state some pressure PA and pressure PB. At the same time, you can state some volume VA and volume VB. Okay, so throughout this isothermal process, the pressure and the volume changes, but the temperature is constant. In other words, in the ideal gas equation, PV equals nRT, this N is the number of moles. So we assume that no gas molecules can enter or exit the container. So we're maintaining the number of moles of gas that's constant. R is just a constant, ideal gas constant, universal gas constant. And T, the temperature is constant in an isothermal process. So PV is equal to constant. And the PV graph in an isothermal process is called an isotherm. So this diagram shows you two isotherms. Okay. For each isotherm, we represent that with a PV graph. The characteristic of an isotherm is, of course, during this isothermal process, the temperature is constant, but between these two isotherms, the isotherm towards the left will have a lower temperature. So if you have another isotherm, say if you draw another isotherm here, this will have, for example, among these three isotherms, that isotherm will have the highest temperature among these three isotherms. Okay. All right, so we said that we want to find how the internal energy of the gas changes during each of the thermodynamic processes. For the isothermal process, note how the internal energy is directly proportional to the temperature of the gas. Okay? But during an isothermal process, the temperature doesn't change, right? Delta T is equal to 0. because the temperature is constant, and therefore the change in internal energy will have to be zero as well. Right. Okay. So the consequence of that, the consequence of an isothermal process where the change in temperature is zero and the change in internal energy is zero, is that so this first law of thermodynamics becomes zero is equal to Q minus W. In other words, the work done by the gas is equal to the heat added to the gas. Okay. So if you think about the first law of thermodynamics as conservation of energy, during an isothermal process, whatever heat is added to the gas goes into the expansion of the gas. So when the gas expands, it does work. So the heat added to the gas is equal to the work done by the gas in expanding. Heat input, this Q is energy input in the form of heat. This work is the energy output in the form of work done. The input energy is equal to the output energy. And in other words, the change in internal energy is equal to zero. Right. Does that make sense? Okay, so in an isothermal process, whatever energy comes in as in the form of heat goes into work that the gas does in expanding, and therefore change in internal energy is equal to zero. Now the next question is, how do we find this work, the work done by the gas? So in any process, if you look at the PV diagram, the work done is equal to the integral of P times dV. It's essentially because in your PV diagram, the pressure is on the y-axis and the volume is on the x-axis. So essentially, the work done is the area under the isothermal graph in your PV diagram. Mathematically, we express the work done as the integral from volume A to volume V of pressure times the change in pressure and the change in volume. Right. So in order to find the work done, we need to evaluate this integral. Okay? We cannot just take out P from the integral, because notice how in the PV diagram, the pressure also changes, right? You have some PA and PV. So throughout the isothermal process, the pressure of the gas changes. So we cannot just take out P out of the integral, but we know from ideal gas law equation that P is equal to nRT over V. So we can substitute, I'll do this step, this into the equation. And so you have the integral of VA VB of nRT dV over V. Right? So all we did was to express the pressure in terms of the volume, because the pressure changes, and the change in pressure also depends on how the volume changes. Once we write out this equation here, then it's clear that nRT, they're constants, they're not affected by the change in volume. So we can take them out of the integral, and you're left with nRT and taking the integral of dV over V. Okay, some calculus revision will tell you integral of dx over x is ln x. Okay, so integral of dv over v will be ln, or natural logarithm of v. Evaluate that from va to vb. you essentially have LNVA minus, ln B minus LNVA, which we can write down as LNBB over BA. Okay, but that's the derivation bit. If you're interested with derivations, the final form will be that the work done will be a function of the initial and final volumes. So you have nRT, and the number of moles times universal gas constant times the temperature. Temperature is constant all throughout, so it's just a single number, but the volume changes during isothermal an isothermal process. Right, how do we interpret the work? Okay, so this is the equation for the work done, and you can always substitute the final volume and the initial volume and the temperatures in order to find the work. Interpretation of the work in terms of what's happening to the gas depends on whether you get a negative work or a positive work or a negative work. When the value of work that you obtain is positive or greater than 0, that means that the gas is expanding. Okay, if we look at, you can look at this and rationalize this several ways, right? If the gas expands, the final volume will be greater than the initial volume, right? So in the first case, final volume will be greater than the initial volume because the gas expands. Yeah, it goes from a small volume to a big volume. Final volume greater than initial volume means that the ratio of BF over VI will be more than 1, and the ln of a number greater than 1 will be positive, and hence you get a positive work. And that's when the gas has done work by expanding. Right, so that's the case where the volume increases. The direction of your isothermal process should be in that direction. You have expansion of the gas leading to positive work. Okay, so notice how during expansion, VB will be greater than VA. The final volume will be greater than the initial volume. Good. All right, the opposite is when the gas, when work is negative, then that implies that the final volume should be less than the initial volume, because then if you get the ratio of the final volume to the initial volume, that's less than 1, and ln of any number less than 1 will be negative. So you'll get a negative work here, but that will be the case when you're going from a big volume to a small volume. So it's this process here. The arrow will be reversed where you have compression of the gas, and that gives you negative work. Right. Okay, so one thing to note, if the gas expands, that means that the work is done by the gas. And when the gas is compressed, the work is done on the gas. And we can sort of think of this logically, because expansion of the gas is when, for example, you heat up a gas. They have a balloon. Don't know if you still remember the balloon dipped into the liquid nitrogen, right? Balloon dipped into the oh, well, no, that's change in temperature. Let's imagine the balloon inside the vacuum pump. because then right when we take out the air out of the vacuum pump, the balloon expanded. And that's because there's no more pressure around the balloon. And so the work is done by the gas molecules inside the balloon pushing out on the walls of the balloon, so that the work is done by the gas when the balloon expands. On the other hand, when the balloon compresses, it's the air molecules around the balloon that pushes inwards, causing the balloon to compress. And that's why during compression, the work is done on the gas, because you need external pressure to compress the gas, whereas during expansion, the gas can expand by itself. It's the gas pushing on the walls of the container outwards, causing the container to expand. All right. Okay, so keep that in mind, because in all the processes, you will always encounter negative work and positive work. And you need to be able to interpret what negative work and positive work means. When you get negative work, that means that the gas compressed and the work is done on the gas. When you get positive work, that means that the gas expanded, and that means that the work is done by the gas when expanding. Right. Okay, so let's look at this example of an isothermal process. Suppose you have this much gas, 2.6 moles of an ideal gas. The initial volume is 3.5 cubic meters. And it's allowed to expand isothermally. That means the temperatures are the same. The temperature is kept constant at 290 Kelvin, but the gas expands to a volume of 7 cubic meters. And we want to find the work done by the gas, the heat added to the gas, and the change in internal energy of the gas. And I'll just put that in here. Right, so the isothermal process is represented by this PV diagram. You're given the initial and the final volumes. The gas expands, so that means the direction of the isothermal process is this way, where you're going from a small volume to a large volume. Right, so we don't know the initial and final pressures, but we can still find the work done in this case in expanding the gas, because that's nRT ln of the final minus divided by initial volume. Sorry, yeah. Right, we're given the number of moles. That's 2.6 times universal gas constant is 8.314. That's a constant number, and then the change in the volumes are given. So you have 7 divided by 3.5. You're doing final divided by initial volumes. Oh yes, I did forget the temp. So, okay. So that's Ln, and the temp is here 290 Kelvin. Yes, thank you. And that should give you a positive 4345. You can see it directly because 7 divided by 3.5 is greater than 1. So you should get a positive work, right? What does a positive work mean? The work is done by the gas or on the gas when it expands. So the problem also says the gas expands. Yeah.
I'm not sure if I'm interested something correctly, but I'm getting 4,777.
4,777 to, yeah, okay, maybe you're right. I have to check my numbers here. 7 divided by 3.5 times 290 times 8.314 times 2.6 gets 4345. So I'm not sure. Try to do Ln bracket 7 divided by 3.5. Yeah, and natural logarithm Ln.
It must just be my format, sorry.
Yeah, the bracketing might be the bracketing thing. Okay, so work is positive. That confirms that the gas expands. A positive work means that the work is done by the gas in expanding. Oops. Right. So when the gas expands, the gas pushes on the walls of the container. So it's the gas that's doing work when it expands, and that's why you have a positive work. Okay. Right, so heat added to the gas. This is Q. Q only comes into the first law of thermodynamics from the change of internal energy is equal to Q minus W, the heat added to the gas minus the work done by the gas. Right, in an isothermal process, the change in internal energy is 0 because the temperature doesn't change, as we've seen in the previous slide, and hence the heat is equal to the work. Okay. So heat will therefore be also 4345 joules. Right, it's positive. What you get is positive heat, and that confirms that heat is added to the gas. And change in internal energy, this is a conceptual question in an isothermal process because the temperature doesn't change, the internal energy doesn't change as well. So change in internal energy is 0. Okay. Good. What happens in the reverse process where instead of expanding the gas is compressed? Okay. So instead of going from 3.5 cubic meters to 7 cubic meters, the gas is compressed so that its volume goes from 7 cubic meters to 3.5 cubic meters. What's the work that's done to compress the gas? Yeah, it will just be the negative. So you still get the work from here. It's just the final and the initial volumes will change, and the effect of that will just to make the Ln negative, and hence the work will be negative 4345 joules. Okay. So the negative sign means that the work is done on the gas. Okay. What you can see here is the conclusion where the work done by the gas is equal to the negative is equal to the negative of the work done on the gas. Okay. So once you find one, either the work done by the gas, you sort of already found also the work done on the gas. It's just, they're just negatives of each other.
So we're heating up the gas, but it's not changing temperature.
Yes, and one way it can happen is it expands in volume. Yeah, and when it expands in volume, the gas molecules sort of are more spread around so that they don't heat the walls so much, and the temperature is constant. Good. All right, second process, the isobaric process, constant pressure. Okay, but in the isobaric process, the temperature and the volume of the gas changes. And one way of achieving an isobaric process is to put a constant weight on a flange, an expandable flange, so that the pressure is kept constant. Pressure equals force over area, right? So you have this constant force being exerted on the gas. The pressure is kept constant, and the constant pressure results to just the change in temperature as the volume changes. Okay, how does the PV diagram or pressure volume diagram of an isobaric process look like? Essentially, you have a constant pressure and the volume changes. So you have here VA going into VB. So the volume changes, but the pressure stays the same throughout the isobaric process. Okay. The work done is still defined as integral of pressure dV, PdV. In this case, it's easier to evaluate this integral now because pressure is constant. So you can take it out of the integral. So you're just evaluating the integral of dV, which is only V. Integral of dV is equal to V. Evaluate that from VA to VB. Hence, you have work is equal to pressure times the change in the volume. You can also see that that's equivalent to getting the area under the PV diagram of the isobaric process. And just like the isothermal process, if the work you calculate is greater than 0, that means that the gas expanded because your final volume is bigger than your initial volume. And when the gas expands, the work is done by the gas. When the work you get is negative, that means that the final volume is less than the initial volume, and that's equivalent to compression. When you compress the gas, the volume decreases, hence final volume is smaller than initial volume. That gives you negative work. Negative work is due to compression and work done on the gas. When you compress a gas, you do work in compressing the gas. So it's still the same convention as for the isothermal process. Good. Right, let's look at an example of an isobaric process. So a gas is enclosed in a cylinder. It's fitted with a light frictionless piston, but it's maintained at atmospheric pressure. Okay. Pressure is constant in an isobaric process. 5,225 kilojoules, or effectively 5,200,000. Yeah. Yeah, convert this to joules in essence, because you're given kilojoules. I think many of you learned the lesson during the workshop to be conscious with the units. Kilojoules need to be converted to joules. That's the amount of heat that's added to the gas, and as a result of adding heat to the gas, the volume increases from 12 cubic meters to 18.2 cubic meters. You see here that the volume increases, so that's the expansion of the gas happening. You want to find the work done by the gas and the change in internal energy as the gas expands. And same problem here. I'll just draw the PV diagram. So that's pressure and volume. The pressure, that's pressure in pascals and volume in cubic meters. The pressure is maintained at 1 atmosphere, 101 times 10 to the 5 pascals. The volume changed from 12 cubic meters to 18.2 cubic meters, right? You have effectively an expansion because you're going from 12 to 18.2 cubic meters. So this is your isobaric, the direction of your isobaric process. The work done by the gas in an isobaric process is pressure times the change in the volume, or yeah, effectively getting the area under your isobaric graph. Okay, the pressure is kept constant. That's at 1.01 times 10 to the 5 pascals. The volume, change in volume is of course final minus initial. So you have 18.2 minus 12 cubic meters, right? And that gives you work equal to 6 to 6.2 kilojoules, or essentially, yeah. Right, you get positive work. So just like in isothermal process, positive work means that the work is done by the gas. Okay? The gas expands. Right, next you want to find the change in internal energy. So you've got the work, you've sorted out the work, and the problem gives you some heat that's added to the gas. So you have the change in internal energy can take two forms, right? You have 3/2 nR delta T, or the change in internal energy can also be obtained from the first law of thermodynamics, Q minus W. This first equation, 3/2 nR delta T, is from the kinetic theory of gases. This is useful only if you know the change in temperature. In an isobaric process, the temperature does change, but we have no clue what the initial and final temperatures are. So we really cannot use this equation from the kinetic theory of gases. What's more useful is the first law of thermodynamics, because we already know the work that is done by the gas, right? And the heat that's added is 5225 joules minus the work 626,200 joules, okay, giving you a change in internal energy of joules. Hope I'm correct. Yes. Right. Okay, and then there's a follow-up here. What if 5225 kilojoules, which is the is removed? So in the first question, you have heat that's added to the gas, okay, that results to the expansion. So in the first question, heat is added to the gas and that results to the expansion of the gas, increase in the volume. How about if you do the process in reverse, so that the same amount of energy is removed from the gas and as a result, the gas is compressed? How much work is done during this compression? Yeah, so the work is still 626,200 joules, but the work will be negative, right? Because you're compressing. Work done on the gas to compress it is equal to the negative of the work done by the gas, hence negative 626,200 joules, right? Good. Okay, right, so we've done isothermal process, isobaric process, and the third one is isovolumetric or isochoric process. In this case, the volume remains constant. What changes is the pressure and the temperature. So you can achieve this by putting the gas in a rigid container so that the volume stays fixed. The volume of the gas follows the volume of the container. So any energy that's added goes into increasing the temperature and the pressure of the gas. Right. The PV diagram looks like this. Y-axis is pressure, x-axis is volume, always in a PV diagram. But the volume is constant, so it's still the same volume all throughout the process. The pressure changes, of course. So if you get the work done by an isovolumetric or isochoric process, since the volume doesn't change, then dV or delta V will be equal to 0. Okay. Hence, the work done during an isovolumetric process is always 0. Okay. In other words, work is done only if the volume changes because of this dV. What happens then is, because we said that work is equivalent to the output of energy from the system. Okay. But because work is equal to 0, then any energy that's put into the system goes into the change in the internal energy of the system. Right? There's only input in the form of heat, and there's no output in the form of work. Hence, the change in internal energy of the system will be equal to how much energy is put into the system in the form of heat.
Question.
Yeah.
Might be a dumb question. I feel like it's a dumb question.
No, it's okay.
It's more related to what we talked about previously with the change in volume. So
Yeah.
theoretically, if you've got a vacuum,
Yeah.
you could use radiation to heat up whatever is inside of that vacuum.
Yeah.
And the change in temperature would cause a change in volume. But in that case, the pressure is 0. And if work is equal to pressure times the change in volume, then wouldn't work be zero? But then how would you end up with a change in volume if you're not doing any work?
Yeah, but this is vacuum, right? So you don't have, so your assumption there, we're saying pressure is zero, is there are no molecules. Because the pressure comes from the gas molecules hitting the walls and exerting force. So when you say vacuum, there's essentially no gas
So you
inside.
wouldn't get the change in volume in a vacuum.
No. And you wouldn't also get a change in temperature because there's nothing that will absorb. There's no gas inside that will absorb the heat. It will be the walls of the container that will heat up.
But isn't that
But
how, isn't that
inside-
how the sun has to travel through a vacuum?
Oh no, but the traveling through the vacuum is through electromagnetic waves. You're not really expanding.
Yeah.
You're not really changing the temperature of the outer space due to the radiation traveling from the sun to the earth,
Right.
right?
I see.
Yeah.
I see. No, yeah.
Yeah. Okay, good. Right, so isovolumetric process work is zero, and so any heat that goes into the system goes into the change in the internal energy. All right. All right, so we've now dealt with the three processes. Adiabatic process is when temperature, volume, and pressure changes. And I think I will leave this to tomorrow because in our lecture tomorrow, we're still talking about adiabatic processes. And instead of rushing through this, I'll just do the adiabatic processes together with tomorrow's lecture, which still looks at adiabatic processes anyway. So I'll just bunch that lecture tomorrow with the adiabatic process today. So yes, so I will see you in the lecture tomorrow and have a good day, everyone.